We've got a question here asking us to consider a couple of simultaneous equations, and we need to find out where there is a unique solution, no solution, or infinitely many solutions. So it's worthwhile knowing what each of those mean. First of all, a unique solution just means that there's a different gradient, because in the Cartesian plane, if the gradients are different, they're going to meet somewhere. Who knows where, but they're going to meet somewhere, and they're going to meet once. They're not going to come back and meet a second or third time. No solution here, that means they're parallel, which therefore means they've got the same gradient. But if they never meet, they're going to have a different y-intercept, because then they have the same gradient, but they're not the same line. So therefore they'll never meet. And infinitely many solutions means that they are the same line. And if they're the same line, that means they've got the same gradient and the same y-intercept. So considering we're looking at different gradient, different y-intercept, same gradient, same y-intercept, what we might consider is to go back to what we know about straight lines and use our y equals mx plus c for a straight line. Because what that would mean in this context is that here, m of the first one doesn't equal m of the second one. For here, m of the first one will equal m of the second one, but c of the first one won't equal c of the second one because they're the y-intercepts. And here, the m's will meet, or the m's will be the same, and also the c's will be the same. So this is ultimately what I'm looking for when I'm going to solve this question. So the first way that I might choose to solve this is using y equals mx plus c, and therefore turning my equations into that. So I could therefore say that equation 1, my first one, becomes y equals negative m minus 2x plus 2. And on my second one, I could say that therefore 2y equals negative mx plus k, and therefore y equals negative m over 2x plus k over 2. So I'm going to use these two equations to start solving this question. Here's my number 1, and here's my number 2. For a unique solution, A, therefore, because the two gradients don't match, I know that therefore negative m minus 2 won't equal negative m over 2. I've got them because these are my gradients of each of the straight lines. So therefore, negative 2 outside of m minus 2 doesn't equal negative m. I'm going to multiply both sides by negative 1, and I'm going to get that. So 2m minus 4 doesn't equal, I need to keep that right, doesn't equal m. So therefore, m can't equal 4. So now I know that m doesn't equal 4 if we're going to have a unique solution. So therefore, I know that for no solution or infinitely many solutions, I know that m would need to equal 4. So this is the first part of my question. I'm going to save this part of the answer. So now let's have a look at part B. Here I'm looking at where my gradients are the same, but my y-intercepts are different. So therefore I can say, well, here I know that m equals 4 because I've already worked out that that means they have the same gradient, which is what I'm looking for no solution. But we need to make sure our y-intercepts are different. So let's substitute this into the two equations. When m equals 4, 1 becomes y equals negative 4 minus 2. So that'll be negative 2x plus 2. And equation 2, when I substitute m equals 4 in, will become y equals negative 2x. That's a good thing because we want the gradients to be the same, plus k over 2. So our gradients are the same. That's great. When m is 4, our gradients are negative 2, but we need our y-intercepts, which are these numbers here at the end, we want these to be different. So for no solution, 2 cannot equal k over 2, and therefore k cannot equal 4 as well. Coincidence that it's the same number. Okay, so if my answer for B will be, there is no solution when m equals 4 and k doesn't equal 4. And just the 4's there, as I say, are an absolute coincidence. It therefore follows that there are infinitely many solutions when we have the same line. That means there would need to be an equal sign here rather than a not equal sign. So therefore my answer to part C will be that there are infinitely many solutions when m equals 4, so the gradients are the same, and the y-intercept are the same, so therefore k equals 4. And that's how we're going to answer a question like this, using simultaneous equations. Now, an alternative solution is if we use the determinant of a matrix. So let's have a look at these lines. Again, I'll write them down. M minus 2x plus y equals 2, and mx plus 2y equals k. I could represent this system as matrices, where I have m minus 2, 1, m, and 2 times xy equals 2k. And if I have a look at the determinant of this matrix, I can find out about unique solutions and no solutions. Remember, I have a unique solution where my determinant doesn't equal 0, and I have an infinite number or 0 solutions when the determinant equals 0. And my determinant, these two cells multiplied by each other minus these green cells multiplied by each other. So let's work out what that equals. So here my determinant will be 2 times m minus 2 minus m, which equals 2m minus 4 minus m. And remember, we're going to have no solutions when this equals 0. So therefore, that will equal m minus 4, and therefore m will equal 4. So we get the same answer looking at the determinant, m equaling 4 for parts B and C, as we did using simultaneous equations and comparing to y equals mx plus c. Now, this is exactly the same way we can arrive at these numbers, but for the y-intercept, we're probably better off going into these simultaneous equations. But it's worth knowing that there are two different ways we can approach this question, and they're both equally valid, and they'll give us the same answer. So with that in mind, here's the tick from the happy examiner. If you found this video helpful, please subscribe or like. Thanks.